Hi friends, we will discuss about the fundamentals of biochemistry from the PDF Voet and Voet. We will discuss only the important part from the exam point of view. So let's begin. The first thing is the important calculation as well as simple also. The enthalpy and entropy of the initial and final state of a reaction system is given. Initial state before reaction, enthalpy is given and entropy is given. Similarly for final state, enthalpy and entropy is given. They have been asked calculate the change in enthalpy and change in entropy. Also, so how will you calculate? So change is del H and final minus initial enthalpy is change in enthalpy. Similarly, final minus initial S, that is entropy, is the change in entropy. Okay. The next question is calculate the change in free energy or for the reaction when the temperature is 4 degrees centigrade. Okay. And is asking is the reaction spontaneous or not. Okay, so they are asking again, is the reaction spontaneous at 37 degrees centigrade or not? So first of all, number B, calculate the change in entropy. How we will calculate the change in free energy, the change in free energy. So for calculating change in free energy, we need to convert the temperature to Kelvin. So we will add 273 degree, 27 plus 273, it was 277 Kelvin. Then the formula for free energy is del H minus T del S. Del G is free energy is equals to del H minus T del S. Okay, del G's value is given. Okay, the del G's value we will take out. How? We know del H, we know T, we know del S. So we will find out the value of del G. Now the value of del G is 180 joule per mole. Okay, which is greater than 0. So if the del G value is greater than 0, it will be an endergonic reaction, that is non-spontaneous reaction at 4 degrees centigrade. Now they are asking find out if the reaction is spontaneous at 37 degrees centigrade. So again the same thing, same formula, just the T will be 3110 Kelvin. Okay, answer is minus 5110. So minus sign is very important here. If the reaction is less than 0, then it is exergonic, which is spontaneous. So endergonic non-spontaneous and exergonic is spontaneous. The next calculation is using the data provided in the sample calculation 1-2, what is the actual free energy? So last time we did about free energy, this is actual free energy where temperature is 37 degrees centigrade and the concentration of A and B are given. Okay, so actual free energy formula is del G is equals to del G plus RT ln B by A. Okay, so this del G, here we have to find out the actual free energy. How we will find out? Let's see. So last time we were calculating del G. Okay, this is the free energy change. And what is this del G0? So del G0 is the free energy change when all of its reactant and product are in the standard state. Okay, so here what we see, say for example, we know the value of del G0, it is minus 15,000 joule per mole, and the value of R is 8.314 joule per mole per Kelvin inverse, and then a T value is 37 degrees centigrade converted into Kelvin, which is 37 plus 273. Then ln B by A, concentration of B by concentration of A. Solving this, we will get the value of G. Okay, another calculation which you can see towards the right side, the standard free energy change for a reaction A to B is this, minus 15 kilojoule. Okay, so here del G0 is a standard free energy change. So they are saying that in the previous question they have mentioned the value of del G0. So this is the previous question, 1.2. Okay, where the value of del G is minus 15,000 kilojoule. Okay, which is converted into joule, which is multiplied by 1000. So what is the equilibrium constant for the reaction at 25 degrees centigrade? So how you will take it out? K equilibrium is equals to e to the power minus del G 0, that is standard free energy, by RT. You have to learn this formula. K equivalent is equals to e to the power minus del G 0, which is standard free energy, by RT. Okay, so e to the power del G value, del G 0, that is standard free energy value, we know. R is 8.314 joule, and K will be Kelvin inverse, and T is 298. So since in the question what is given 25 degree centigrade, we have to convert this into Kelvin, which is 298 Kelvin. So now it's easy to find it out. When we will solve this, we'll get 426. So you have to remember K equivalent is equals to e to the power minus del G0 by RT. Okay, and here for standard calculation of standard free energy, how we will do that? Del G is equals to standard free energy plus RT ln V by A. Okay. So what are the key points of this chapter is origin of life. What we know, that life proposes that organisms arose from simple organic molecules which has polymerized to form complex molecules which replicates themselves. Okay, and then the compartmentalization of organelles, it has gave developed metabolic reactions which allows biological molecules to synthesize and give energy, and cells can be either prokaryotic or eukaryotic, and eukaryotic are more complex, having membrane bound organelles. And phylogenetic evidence shows that there are three domains: archaea, bacteria and eukarya, and natural selection will determine which organism will evolve and proceed further. Coming to thermodynamics, so first law of thermodynamics says energy is conserved. Second says spontaneous process will increase the disorderness of the universe. Okay, and the spontaneity is determined by free energy change, which is del G, but that is free energy change, is equals to enthalpy minus T del S, which is temperature into entropy. And spontaneous reaction have del G less than 0. Okay, and non-spontaneous have del G greater than 0. Greater than 0 is endothermic, less than 0 is exothermic. And the equilibrium constant for a process is related to the standard free energy. You have seen Keq is equals to e to the power minus del G0 by RT. Okay, and living organisms are open systems that they maintain a non-equilibrium steady state, that is homeostasis. Now the structure of water has been very important. Structure of water molecule we need to know. This is the second chapter, water. First we did about introduction of life forms. Second chapter is water. Okay, so here what we see, that van der Waals force is there, then OH covalent interaction is there. There is a bond distance between OH, which is 0.958 angstrom. Okay, and the degrees between the H and H, the angle which hydrogen forms, it is what? 104.5. This we need to remember. Okay, and very interesting part, you can see the structure of H2O. What is the structure? It is tetrahedral. Okay, the oxygen atoms sp3 orbitals are arranged tetrahedrally. You can see that there are two orbitals contain non-bonding electron pairs. Two contain bonding electron pairs, two contain non-bonding electron pairs. So see how a hydrogen bond is formed between two water molecules. So hydrogen bond is represented by a dotted line here, this one. It is represented by a dotted line here. So the strength of the interaction here, it is maximum when the OH covalent bond of one molecule, when the bond of one molecule points directly towards the lone pair of the other, this one. Okay, so you can see the OH of one points directly towards the lone pair of the other. Here OH of one points directly towards the lone pair of the other, then the interaction is maximum. Next, coming to the structure of ice. So each water molecule interacts tetrahedrally with four other water molecules. Okay, Next, coming to bond energies in biomolecules. So covalent energy is the highest, among which the OH is the highest. Okay, OH, then it is CH, then it is CC. So OH, oxygen hydrogen, is the highest energetic bonds. It's very hard to break. Then it is CH, then it is CC. Then comes the non-covalent interaction, which includes ionic, van der Waal, hydrogen, dipole, and London dispersion forces. So among the non-covalent, ionic is the highest. After ionic, it's van der Waal. After van der Waal, it's hydrogen bond. Okay, which is OHO. So don't consider OH as a hydrogen bond, which is in under covalent bond. So it is OH, and with the lone pair of other molecule. Okay, it's hydrogen bond. Okay, then dipole interaction, then London dispersion. Then another very simple calculation, it says that 1 into 10 to the power minus 4 mole of H plus as HCl is added to 1 liter of pure water. Determine the final pH of the solution. So if you add any solution, maybe H plus or OH, to the pure water, then what will be the pH? So pure water pH is 7, we all know. So if we add the acidic molecules, it will become acidic. So whatever number of hydrogen molecules we add, it will show that pH only. So the total is therefore 1 into 10 to the power minus 4 only. And this we can say it as the formula to determine the pH is minus log of number of hydrogen concentration or hydrogen concentration. So minus log, we know 1.0 into 10 to the power minus 4 number of hydrogen molecules has been added. So pH will be 4. Now another very simple calculation. Calculate the pH of a 2 liter solution containing 10 ml of 5 molar acetic acid and 10 ml of 1 molar sodium acetate. We have to calculate a pH of 2 liter solution which have 10 ml of 5 molar acetic acid and 10 ml of 1 molar sodium acetate. So first of all, what we will do, we will calculate the concentration of acid and conjugate base, which express all the concentration in units of moles per liter. We will find, so here it's given in ml and moles. We have to find out in moles per liter. How we will do that? So 0.01 liter by into 5 molar by 2 liter. So how much of the 2 liter is this 10 ml and 5 molar? Okay. Similarly, like for 10 ml, we have written 0.01 liter divided by, into 5 molar divided by 20 liter. So we will find that out of 2 liter, in 2 liter, the acetic acid concentration is 0.025. Similarly, for sodium acetate, what we will do, 10 ml is 0.01 liter into 1 molar divided by 2 liter. So we are finding the concentration. How? Okay, out of like in 2 liter, how much is sodium acetate? So we are doing 10 ml, which is converted into 0.01 liter into 1 molar divided by 2 liter. Okay, now the formula is to find out the pH, we will use Henderson-Hasselbalch equation. Okay, now how we will solve it? pH is equals to pK plus log of base by acid. Okay, conjugate base by conjugate acid. So acid by conjugate base. Okay, so here pH is given to us. Okay, what is the pH given to us? Here it's saying for find out the pK for acetic acid in table 2 to 4. So see, pK for acetic acid is given, which is 4.76. Okay, we will put this in our equation. So pK 4.76 we have put exactly like that, plus log of acetate, the concentration of acetate by the concentration of acetic acid, and we got the final pH. So this will be given to you, 4.76, that is pK of acetic acid. This will be given to you already in the question. Okay, so very easy to find out the pH when the concentration of the conjugate base and acid are given. Okay, we'll use Henderson-Hasselbalch equation. Next question is calculate the pH of 1 liter solution containing formic acid, which is 0.100, and formate, that is sodium formate, which is again the same concentration. So concentration of formic acid and formate are same here. Before and after addition of 1 ml of 5 molar NaOH. It's asking how much would the pH will change if the NaOH were added to 1 liter of pure water. So first of all, let's simplify it. Okay, first of all, using Henderson-Hasselbalch equation, let's find out the pH. Okay, how to find out the pH first? So here pH is equals to, we all know pH is equals to pK plus log of conjugate base by acid. Okay, so base is formate, concentration is 0.100, and the concentration of formic acid here it's same. So when we will do ln base by acid, okay, then so log of concentration by concentration, so since the concentration is same, okay, it will be 1, and log 1 is equals to 0. Okay, so what if you will write it in the equation form, you'll find it log of concentration of base by concentration of acid, it will cancel out and it will be log 1. Log 1 is 0. And from the table we have to find out that formic acid pK is 3.75. Since log part is 0, we will get pH is equals to pK, which is 3.75. Okay, now coming to the second part, what will happen if 1 ml of 5 molar NaOH is added? So addition of 1 ml of NaOH, it will not significantly change the volume. Volume will not change significantly. Okay, so how much is the change if we calculate? So 1 ml is 0.001 liter into 5 molar divided by 1 liter. Okay, so 1 ml of 5 molar into 1 liter, if it's added, how much is added? That means 0.005 molar. Okay, very less amount is there if we calculate the volume like we did it in the last question. So we all know that NaOH is a strong base. It will completely dissociate into sodium and hydroxyl ions, and hydroxyl ion concentration now we know it's 0.005. Okay, and this 0.005, which is OH minus, okay, NaOH, it will break into Na is equals to 0.005 and OH is equals to 0.005. So this OH will react with formic acid to form formate and water. Okay, so formic acid concentration is decreasing because it is breaking down into formate and water. Okay, so and the concentration of formate increases by 0.005. Okay, it will try to equalize with the concentration of hydroxyl ion. So concentration of hydroxyl ion and the concentration of formate will be similar now. The number of OH ions will be there. It will try to form the same number of formate. So it will try to equalize the number of formate, and it will be 0.005, same as hydroxyl, if you are following me. Now what we found out, that the formic acid has been decreased. So what was the initial concentration of formic acid? It was 0.100. And what is the final concentration of formic acid? So we found out that the formate concentration now it has become 0.005. Okay, that means 0.005 molecules of has been taken out from formic acid to form formate. So we will subtract 0.005 from the initial formic acid concentration. It is 0.095. Okay, so the new formate concentration is what? So formic acid concentration is 0.095. But what is the new formate concentration? We will add whatever amount has been converted, okay, which is equals to number of OH minus ions. Number of OH minus ions is 0.005. Same it will be number of formate ions, which is again 0.005. So 0.005 will number of formate molecules will be added. So we'll add to the initial concentration of formate. So we have subtracted 0.005 from formic acid and we have added 0.005 to the formate. Okay. Now if we try to find out the pH, so log of formate by formic acid. Now formate concentration, the final concentration we found out is 0.105. Formic acid is 0.095. From the table we know the value of pK of this formic acid, which is 3.75. So final pH is 3.79. Okay. So in the absence of formic acid buffering system, okay, in the absence of formic acid buffering system, the pH can be calculated directly from Kw. How? So we all know that H concentration of H plus and concentration of OH minus ion together it forms 10 to the power minus 14. Okay, so to find H plus we can calculate and we can find it out. And OH minus concentration we know. So if the formic acid would not have been in the picture, we could have already found out the pH from Kw. Okay, so if we know the OH, that is 0.005 here from here. If we know the OH value, we can find out the number of H plus ions. Okay, and pH we can just put this value into pH into H plus concentration and we can find it out. So basically if formic acid is not in the picture, then we can use the formula H plus into OH minus. Concentration of H plus into OH minus is equal to 10 to the power minus 14. And we can find out the number of H plus ions. Okay, but if conjugate acid and conjugate base is there in the picture, you have to use the Henderson-Hasselbalch equation. Okay, so whatever the number of molecules have been taken out while it is dissociating, you will subtract it from the initial concentration, and whatever number of molecules have been formed, you will add it to the initial concentration. Then you will find out the final pH using the final concentration of each of them. I hope it is clear. The next question is, how many milliliter of a 2 molar solution of boric acid must be added to 600 ml of a solution of 10 millimolar sodium borate in order for the pH to be 9.45. Seems very complicated, but it is not. Okay, again start with the Henderson-Hasselbalch equation. So what we know from Henderson-Hasselbalch equation is pH is equals to pK plus log of conjugate base by acid. Okay, what is given to us? We know the value of conjugate base, okay, and we know the value of conjugate acid. Do we? So now let's discuss some key points about this chapter. So the main thing that liquid water is an irregular network of water molecules that each form up to 4 hydrogen bonds with neighboring water molecules. Okay, each can form up to 4 hydrogen bonds. Then hydrophilic substances such as ions and polar molecules dissolve readily in water. Hydrophilic can dissolve in water, while as hydrophobic effect is the entropically driven tendency of water to minimize its contact. Okay, it's an entropy driven tendency of water to minimize the contact of water with the hydrophobic substance. Okay, the next is chemical properties of water. So chemical properties, the concentration of H plus in solutions is expressed as pH value. That is pH is equals to minus log of H plus concentration. Okay, acids can donate protons, bases can accept protons, and the strength of an acid is determined by its pK. The stronger the acid, the lower its pK. Very, very important. And the Henderson-Hasselbalch equation, it relates the pH of a solution to the pK and concentration of acid and its conjugate base. We have already discussed that. And buffered solutions resist changes in pH within about 1 pH unit of pK of the buffering species. So buffered solutions, it will resist the change in pH. Okay, so that's it for the first 2 chapters. So let's revise what we did in today's class. We have understood how to calculate the how to calculate the change in enthalpy, then how to calculate the change in entropy, then how to calculate the change in free energy for the reaction, which is del G is equals to del H minus T del S. Okay, then what we learned, standard free energy change, then we understood K equivalent calculation with the help of standard free energy change. Then we learned that if del G is less than 0, it is what, spontaneous reaction, and del G greater than 0 will be non-spontaneous reaction. Then in chapter 2 water, what we learned? We learned about the bond angle between hydrogen and hydrogen, the OH covalent bond distance. Then we understood about the structure of ice, which is tetrahedrally, which interacts tetrahedrally with 4 other water molecules. Then we understood next what we learned about. We understood about the calculation of pH from conjugate base and acid using Henderson-Hasselbalch equation. Then we learned to calculate the pH of a solution, where we added NaOH in extra, and we subtracted the number of molecules which have been converted into OH, and we, with the final concentration, we have found out the pH using Henderson-Hasselbalch equation. And the last question for today's class is, how many milliliters of a 2 molar solution of boric acid must be added to 600 milliliter of a solution of 10 millimolar sodium borate in order for the pH to be 9.45. So first of all, we will rearrange the Henderson-Hasselbalch equation. We all know that Henderson-Hasselbalch equation is pH is equals to pK plus log of conjugate base by acid. So we'll find out first, we will modify this equation, we'll rearrange it, and we will find out the value of the, we will arrange it in that way that we have to find out the concentration of conjugate base by acid. Okay, so it's equals to log of pH minus pK. So we'll substitute the values. We know that pH value is 9.45, and for boric acid it is 9.24. The pK is 9.24. We'll find, and the concentration is 1.62. So what is given, that the starting solution contains 600 ml of a solution. Okay, so into 600 ml of solution and 10 millimolar sodium borate. So we will calculate 600 ml is equals to 0.6 liter and 10 millimolar is 0.01 molar. We'll multiply it, and what we find is 0.006 mole of borate is there. So what we are calculating, we are finding out that the concentration of the starting solution. So starting solution is having 600 ml containing 10 millimolar sodium borate. Okay, so 10 millimolar into 600 is 0.006 mole of borate. We are multiplying, and 600 ml is 0.6 liter and 10 millimolar is 0.01 molar. Okay, so we found out the initial concentration. Then amount of boric acid needed is 0.006 mole by 1.62. So how much of boric acid is needed? So we'll divide it with the conjugate base by acid. So that amount is needed. Okay, but the stock is 2 molar. So volume that can be added is divided by stock. Okay, so what we did first, we found out the concentration of base by acid. Okay, out of which we need to find out the amount of boric acid. So total base by acid is 1.62, out of which we need to find out the amount of boric acid only. So out of the total base by acid 1.62, the boric acid is how much? The boric acid is 0.0037. So with this formula, that conjugate base by acid is equals to what? It is equals to which we found out is 1.62. So what you need to do, if you know the concentration of borate here, that is A minus, if you know the concentration of borate which we calculated as 0.006, if we know the concentration of borate, we can put the value in this equation. So if we put the value of 0.006 in case of A minus, so we can find out the value of HA. Since concentration of A conjugate base by acid is equals to 1.62, which we have calculated. So if we want to find out the value of any one of it, we will have to put the values of the other. Okay. So if we put the value of conjugate base as 0.006, we can find out the value of HA by dividing this 0.006 by 1.62. Okay. So 1.62, which is towards here, we will put it towards the denominator, and we can find out the value of boric acid. So boric acid is 0.0037. So stock is 2 molar. We have to find out how much boric acid should be added to the stock. So this concentration of boric acid divided by the stock, we will find out how much of the boric acid to be added. Okay. So I hope this is clear. So this video, if you will watch again, you will understand. So this part included about the structure of the water molecules, some thermodynamic laws, and next day we'll proceed with the nucleic acid part. Thank you.